Hello guys, how's it going? Mike coming back at you here with another video on number theory. In the previous video, we got into mathematical induction, the mathematical principles behind it, the basis for this technique of a proof, and we went through the statement of each of the steps involved in the three-step process for the proof technique of mathematical induction. Now we're actually going to go through some sample problems to see how we use this proof technique. So we're going to start off with a pretty basic problem. This is a standard first problem that you would see when proving via mathematical induction. And this is a result that you may have already seen before from your previous math courses. We're going to prove for all whole numbers greater than or equal to 1, we're going to show that the sum of the first n positive whole numbers, so 1 plus 2 plus 3 plus, all the way up to and including plus n, is equal to n times n plus 1 all over 2. Now, if we go back to our three-step process, first thing we have to do is show the basis step. We have to show that the statement that we're given is true for the first n value that we can have. That is to say, we need to show that this thing is true for when n is equal to 1. So, what we do is we take this n value and we plug it into each side of this equation, and we want to see that the left and right hand sides do indeed equal each other. Well, if n is equal to 1, then the sum of the first 1 positive whole numbers is just the sum of 1, which is 1. And if I plug 1 in for n on the right-hand side, quickly fix that there. If I plug 1 in here, I get 1 times 1 plus 1 all over 2. And last time I checked, that gives me 2 over 2, which is also equal to 1. So we have our left and our right-hand sides matching. This shows that this statement is true for when n is equal to 1. We have it shown true for the first guy, or we've knocked over that first domino in the long line of dominoes. Step 2 is the which is the hypothesis step. This is always just a single sentence. It's always assume that this thing right here is true for some arbitrary whole number k. Now, there's several ways you can write that, but the main thing that you should do is change the letter that's used from n to k. Actually write out 1 plus 2 plus k is equal to k times k plus 1 all over 2. Make that substitution and just say assume for some k that this thing is true. And this is all that our second step is. It's just writing one sentence. There's no math you have to do. It's just write one sentence. Now, the third and final step, which is the induction step, as I was just about to say before, but didn't want to. We said in the previous video that this is the step that has the most work involved. It is the place where most people are going to get tripped up when they have to prove something via mathematical induction. So what I suggest you do, if you want, is kick off the third step, just writing out to yourself what it is that you want to show. Recall that the third step is that we have to show that the statement that we were given is true for when n is equal to k plus 1. So, what is it that we have to show? I have to show that the sum of the first k plus 1 whole numbers, or our left-hand side here, is equal to this thing, except with k plus 1 plugged in. And we see that when we plug k plus 1 in for n, we get k plus 1 times k plus 1 plus 1, or k plus 2. So k plus 1 times k plus 2, all of that over 2. So this is just me writing out what it is that I want to show, what I have to show in order for the third step to be valid and to be done, and thus for our entire proof to be done. Now, when you're showing that two quantities are equal, you could directly work from one side, start with one side, do some mathematical operations, and get to the other side. Or what you could do is you could start with one side, work it down to some point, and then work with the other side separately and show that it gets worked down to that same point. And then you would know that those two quantities are indeed equal. So that's two ways that you can essentially show what it is that you want to show in the third step. For this particular problem, I'm going to start with the left-hand side and show that this is equal to the right-hand side directly. I'm going to go right from the left to the right without working with two separate chunks of things. So here I started with my left-hand side. This is where your hypothesis step, this is where that sentence that you wrote and what you've assumed in step 2 comes into play. If I just look at this right now, I see, okay, I'm just adding up 1 plus 2 plus 3 plus k plus 1. How am I supposed to turn this into k plus 1 times k plus 2 all over 2? Well, if I look at all of the terms that are in my red bracket there, the 1 plus the 2 plus k, I know something that is all equal to. From step 2, from our hypothesis step, we assumed that 1 plus 2 plus k was equal to k plus 1, was equal to k times k plus 1 all over 2. So I can make the substitution here. I can get rid of all of those terms except that last one and replace it with what I assumed in step 2. That k times k plus 1 all over 2. And the use of your hypothesis almost always, virtually always gets brought into play immediately upon going through the third and final step. So this is just showing what we just mentioned. I made the substitution from what I assumed in my hypothesis step, aka step 2. I'm going to take all of this and turn it into one fraction. I'm going to make this a fraction with the same bottom. So I'm going to multiply this guy by a 2 over 2. And when I do that, I get k times k plus 1 over 2 plus 2 times k plus 1 over 2. Now looking at these two fractions here, each of these guys contains a common factor of k plus 1 on the top. So what I can do is I can pull that common factor out of each of those two terms, and I'm left with k plus 2. So I have k plus 1 times k plus 2 on the top, and that's all over 2. And that is exactly what we wanted to show in our third and final step for this one particular problem. I wanted to show that 1 plus 2 plus k plus 1 was equal to k plus 1 times k plus 2 all over 2. And that is what we did using this short quantity of work. So after you have completed the third and final step, typically we just write a quick little few words just saying, therefore, this statement right here is true via mathematical induction. Or you could say, therefore, the fact is true, or therefore, the statement is true. But look at what we're doing in each of these three steps in the technique of, or in the proof technique of mathematical induction. We're saying, okay, whatever the first n value is, we're showing that it's true for that first guy in step number 1. Step 2, we're assuming that the fact, quote unquote fact, is true for some random positive whole number k, and then we're using that to show that same fact, in air quotes, is true for when we have the value k plus 1. We're going to move on to one more sample here inside of this video. This is the next most common sample problem that you would see. Again, it's going to be for all positive whole numbers greater than or equal to 1, but we're going to show that the sum of the squares of the first n positive whole numbers, we're going to show that 1 squared plus 2 squared plus n squared equals n times n plus 1 times 2n plus 1 all over 6. So again, we're going to start with our basis step. The problem says for n greater than or equal to 1, so that value of 1 is what I'm plugging into each side of this equation here in my basis step. So the sum of the first one, the sum of the squares of the first one positive whole numbers is just 1 squared, which is 1. If I take 1 and plug it in for n here, I get a 1 times a 2 times a 3, which is 6, divided by 6, thus gives me 1. So the basis step is done. We've shown that this is true for n equals 1. Step 2, assume for some positive whole number, some arbitrary positive whole number k, that 1 squared plus 2 squared plus k squared equals k times k plus 1 times k plus times 2k plus 1, pardon me, all over 6. And it's sort of implicitly assumed that we're working with positive whole numbers, so you don't have to say for some positive whole number k, you can just say for some k. And then step 3, which is our inductional step. Just like the previous problem, if you feel that you need to, just write out for yourself what it is that you want to show. What do you have to, what two quantities do you have to show are equal for this particular problem? 3, we have to show that this is that this fact is true for when n is equal to k plus 1. So I have 1 squared plus 2 squared plus k squared plus k plus 1 squared. And when I substitute k plus 1 in for n on the right-hand side, I get k plus 1 times k plus 2 times 2k plus 3. You have the 2 multiplying into both terms in that k plus 1, which gives you 2k plus 2, and then we have the plus 1 at the end. So that's why that third term there is a 2k plus 3. Now, once again, I'm going to start with my left-hand side, and I'm going to show that that we can turn this into the right-hand side. So I'm going to start with that thing there, and I'm going to get it down to that guy there. So just starting off with my left-hand side, again, once you write that left-hand side, this is where your hypothesis kicks in. This is where your hypothesis comes into play. I assumed in step 2 that everything that's in red there, everything except that final term, is equal to some nice particular thing. I assume that it's equal to k times k plus 1 times 2k plus 1 all over 6. So that leads us to here. So we have k times k plus 1 times 2k plus 1 all over 6, plus that final term, k plus 1 quantity squared. I'm going to turn all of this into one fraction. So to do that, I need to multiply on the top and bottom of this term here by a 6. So that leads me to the second part of my second line here. This is equal to k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared, all of that over 6. Now, this first term up top has a factor of k plus 1. The second term on top actually has 2 factors of k plus 1. So what I can do is I can pull a common factor of k plus 1 out of each term on the top. And what that leaves me with is this first part right here. That k plus 1 times, and this is all one quantity, k times 2k plus 1 plus 6 times k plus 1. So we distribute the k into the 2k and the 1, and we distribute the 6 into the k and the 1. We multiply things out, we recombine like terms. That leaves me with k plus 1 times 2k squared plus 7k plus 6, all of that over 6. So all we changed from the first half of this line to the second half of this line was this thing became that thing there. And now, if you take a look at 2k squared plus 7k plus 6, that thing breaks down into some nice factors. We can factor that out pretty easily. And what it factors into is just the missing pieces that we needed. The 2k squared plus 7k plus 6 breaks down into k plus 2 times 2k plus 3. So that entire quantity is k plus 1 times k plus 2 times 2k plus 3 all over 6. And that is the right-hand side of what we wanted to show. Up top, we had the left-hand side. You can go back to that slide if you want, and we see that right here. So this is the end of our inductional step. This is the end of the most complicated step of all 3. Now we'd wrap it up with just a nice little few words saying, therefore, the fact is true, or therefore, the statement is true, by mathematical induction. So these are a couple sample problems for you to see how this technique of mathematical induction gets used. You'll be seeing some of these problems on your homework. You'll be seeing them maybe on a quiz. You will also be seeing one of these guys on your first test. These make for very, very good test questions. If you feel like you need to see more problems and you're not sure where to turn to, feel free to get in contact with me and I will provide you with some extra resources. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, folks, take it easy.